Hello, I'm Amit, and today I would like to talk about partitioning and the state of partitioning in latest Postgres. I'm a software developer and have been contributing to Postgres open source project for a while now. As for my day job, I'm a Postgres architect at Enterprise DB, where my main focus is open source Postgres development. Before Enterprise DB, I worked for an entity in Japan where I did similar things. The intended audience of this talk is anyone who knows databases or have heard the term partitioning but not sure what it does, or maybe even have used partitioning but would like to learn more about it in the context of Postgres. Here's a brief outline of this talk. At first, I will describe some general points about partitioning, such as what it is and why not to use it. I will mention certain situations where it is especially useful and also mention some of the benefits of partitioning in general. Then I will describe the partitioning support in Postgres. So at first, I will give a brief note on the historical implementation of partitioning in Postgres, and then the modern one introduced in Postgres 10, and subsequently improved significantly in versions 11, 12, and 13. So when talking about the new partitioning, I will describe the syntax for partitioning, how partitioning works with features like indexes, constraints, triggers, replication, etc. And also, as I consider the optimizations that are enabled by partitioning to be an important part of the partitioning feature, I will cover each one that I know with examples. I will end this talk by sharing some of the best practices and pitfalls to remember when using partitioning. All right, so what is partitioning? So in this talk, by partitioning, I mean a set of features that allow you to deal with big tables, large tables more conveniently. So how big is too big? Think over a terabyte or maybe more. And these partitioning features also let you deal with some of the data loading and deletion patterns more conveniently. So with partitioning, you take a large table which represent a single logical relation into physical pieces that are individually smaller, and each such smaller piece is called a partition. And you also describe using some syntax what subset of data that each partition will contain. And this division of data into partition can be either manual or automatic, but it's always based on a notion of partition key. So a partition key is a column or a set of columns whose values will tell which partition to assign that row to. It's difficult to divide the key space into ranges of values where you specify a minimum and maximum for each partition, or lists of values where the partition key will have only a fixed set of values for the given partition. So the range and list approach typically map to some queries in the application that you want to optimize. For example, with range partitioning, you can optimize a query to get sensor measurements in a given time interval. Or you can use list partitioning to optimize a query that queries your measurements using only the sensor ID. So sometimes none of the table's columns have that property of being useful to optimize some queries, but you still want to distribute your data. So hash partitioning can be useful in that case. So with hash partitioning, you take a column or a few columns and take their values and use a hash algorithm to create a hash value from those values. And these hashed values are assigned to buckets almost randomly, or sometimes using something more predictable like round robin algorithm. And what that does, you get a uniform distribution of your rows, so which is a property of partitioning. So that sounds great, right? I mean, it does sound like partitioning can be useful, because why do all that work? Instead, you can just store your data in a single table. And more often than not, people tend to use partitioning for the wrong reason to begin with. For example, they think that the performance improvement is the main benefit of partitioning, but you have to consider that the performance benefit you get from partitioning, you can also get using some of the other tools like indexing. So you should try those things first before you use partitioning, because once you implement partitioning, So everything else beside that narrow set of cases where partitioning is useful, everything else can become negatively affected. So you have to be careful. Well, having said that, let's shift our focus to things that our partitioning is actually useful for or worth experimenting with. So consider if you have a use case in your application where you have to load data or delete data from your table, from some table in batches. So you would use insert or copy to do the load and delete to do the bulk delete. But those things can be very time consuming, and you don't want that time consuming aspect in your application. So partitioning is worth considering for that problem. So with partitioning, you substitute that insert and delete, which can take quite long, with simple DDL commands. And these DDL commands can be instantaneous if you manage the timing well. That is, you run them at a time when the DDL commands can get the locks, and once they get the lock, they can finish instantaneously because it can only be a metadata change. So next is the headaches of maintenance jobs. So I hear that some of these maintenance jobs on large tables can take days to finish, but with partitioning, these maintenance jobs can run on individual partitions. And because these individual partitions are smaller, they can finish faster. So by maintenance jobs, I meant things like vacuuming or reindexing and stuff like that. And because the maintenance jobs can run on the granularity of individual partitions, you have the option to run these jobs on less active partitions at any given time. So you lessen the disruption due to this maintenance activity. And finally, there is performance. So consider that for OLTP queries, the buffer manager can be a big bottleneck, because with a large table, your data can be on the disk in any arbitrary location. So there is no locality of access. So your queries may end up spending a lot of time shuffling data between the shared memory buffers and disk. But with partitioning, queries tend to be focused on a small set of partitions, and because these partitions are smaller, there's a good chance that they fit in memory, and the shared buffers manager is no longer a bottleneck. So it's not just these short queries that are get this benefit from partitioning, but also the more complex analytics queries. So these more complex queries that I'm talking about will have joins and aggregations and many of them, and these joins can be very expensive when they're running on these large tables. So with partitioning, these joins can be pushed down to individual partitions, and if you consider parallel execution, combined with parallel execution, these joins on partitions can finish much faster than a big join on a large table. And Postgres does have some advanced capabilities in this area, which I will describe later. All right, so let's look at how much Postgres can handle of what I just described. So let's take a look at first some history of partitioning. So you may have heard that there has always been support for partitioning in Postgres, and that's true to some degree. So it was Postgres 8.1, which was released in, I think, 2005, that included a feature called constant exclusion, which allowed Postgres to optimize queries on partition tables. And these partition tables would be implemented using something called table inheritance. And well, it worked for people for a lot of years, but people always knew that these features by themselves are not enough to call this whole setup an actual partitioning feature. But yeah, I mean, let's take a look at how an implementation of older partitioning might look like in practice. So as I said, you would use table inheritance to create a bunch of tables in parent-child relationship, where the parent is the logical placeholder relation, and the children or the child tables are what actually contain the data, and they are the partitions. And to get the benefit of constant exclusion, the feature that I just mentioned, you need to add a check constraint on each child table which tells the optimizer which data it contains. So the optimizer can decide whether or not to scan a given child table for a given query. So, child tables can be filtered out based on the query's where filter. On the right-hand side, I show a trigger that is defined on the parent and a function that is called by the trigger. So the function takes a row that is inserted into the parent, and it checks its designated partition key columns to decide which child table to insert it into. So you get, data distribution with this trigger and this function. But remember, as a user, you have to, make sure that the check constraints and triggers are defined correctly, especially considering as you have to add, new partitions. If you miss doing that, or if you make a mistake somewhere in all of this, it's, you can guarantee that partitioning is working correctly. So it was Postgres 10, that was released more than a couple of years ago, that first introduced a syntax for partitioning. And once the syntax got in, the partitioning feature started to look more like a native feature, because subsequent releases, made these capabilities even stronger. And that's what I'll be describing in the coming slides. Excuse me. So let's start with the syntax of declarative partitioning. To use partitioning, you must use a specific syntax to create tables and do some other operations that are related to partitioning. And the syntax, I think, is pretty intuitive, but you may agree or disagree based on your background with partitioning. Anyway, so to specify that a given table will have partitions, or to make that table a partition table, you have to specify a partition by clause. So in this example, you can see that I'm creating a range partition table with partition by range. And by specifying log date here, I'm saying that each partition will have a specific date interval or range of log date in that partition. And by the way, the table that is defined with partition by clause, which I just called a partition table, is also called a parent table in older terms. Next, you can see individual partitions definitions. The for values clause tells what interval each partition is for. And these partitions are sometimes called child tables. This child and parent terminology is somewhat of a legacy of the old partitioning. Okay, so if you want to use a sub-partitioning, that is multi-level partitioning, you can use partition by clause again on the partition when defining partitions, and then create partitions of these partitions. So, you can go as deep as you want to go with this, but 2 levels is often enough. So from version 11, you can also create hash partitions that I've shown here on the right. So as mentioned before, hash partitioning, there is no meaningful boundaries to assign to each individual partitions, but you still have to create these partitions, by yourself. And here in the syntax that I've shown here, the modulus, it gives the total number of partitions, and the remainders are like the bucket numbers that are assigned to each partitions. And the modulus is the more important figure here, which gives the total number of hash partitions, which is the thing you care about with hash partitioning. And by the way, you can combine these range list hash any way you like when creating multi-level, partitioned hierarchies. So one more feature I forgot to mention that I've shown here on the left-hand side is the default partition, which you can create for list or range partitions. So normally, Postgres would give an error if there is no partition defined for a given row. But if these errors are annoying for you, you can create a default partition. What it does is for rows that don't have any other partition defined, those rows are inserted into the default partition. And later, if you define the actual partition for that row, you have to move those rows from the default partition into the actual partition that is appropriate for that row. And unfortunately, Postgres doesn't do this automatically. One often useful feature is multi-column partitioning, which can be used with range and hash partitioning, and it's often a substitute for multi-level partitioning with its own benefits. It can be a bit tricky to understand, so let's take a look at an example of range multi-column partitioning. So imagine you have a table to store cells, which covers sales records from different stores. And assuming this is going to be a big fact table, you might want to partition it on using something. So you choose to use range partitioning on store ID, but then you consider that some stores might be more popular and have more sales. So the partition for some stores can become like larger than others and can become a hotspot. And to avoid that, you also want to use some other column to subdivide those only those partitions. And you could use multi-level partitioning, but here I'm showing how to do the same thing with multi-column partitioning. So you use store ID as the first partitioning column and sale date as the second partitioning column. And with that, you can have different partitions with the same value for the first column, and it's the second value that determines the target partition for any given row. So here the store ID 1, which in my hypothetical example is more popular, has a partition for each month. So in this case, the partition for a row is determined by first selecting the store, and then by looking at the sale date, you can get the correct partition for this row. So anyway, if you can manage to wrap your head around all this, then I think it's better than can be better than multi-level partitioning, because having fewer levels can give a small performance improvement there. Moving on, more on the syntax. So there is a command to take a standalone table that is compatible with the target table, that is have the same schema, and you load your data into it. You validate that data by using, say, check constraints, and then using a single attach partition command, you make that a table, a partition of your target table. And what this does for you is it allows you to load data using a simple DDL command instead of doing insert. And from version 12, this attach partition command takes it doesn't block other operations because it takes a slightly less stronger lock than the strongest lock that was taken before. So this attach partition command doesn't block your normal queries. So you get the loading without disrupting your other operations. And for batch deletion or removal of data, you can use detach partition. And you could have used a drop table if you didn't want that data. But if you want to keep the data around, then using detach partition will allow you to simply remove that partition from your target table and keep the data around if you want it around. So anyway, that's all the syntax there is. So let's take a look at some of the other things that are related to partitioning. Excuse me. Indexes. So maybe you already know this. Indexes can be useful for mainly two things: to enforce constraints like unique, and more commonly to improve the performance of queries. So using partitioning does not preclude the use of indexes, as I said before. Actually, it can be useful to combine partitioning and indexing where it makes sense. But indexing becomes a bit complicated when you start using partitioning, as I described below. So each partition can have its own indexes, and they can look different on different partitions based on the queries that hit different partitions in a different way. And you can even drop these indexes freely as you want. But some of the indexes need to be present in all partitions that are common to all partitions, and they can be defined by creating them on partitions directly, or even using a shortcut, which is to create it on the parent table, and Postgres will make a copy of that index in each partition. And this feature is present from version 11. With Postgres, with version 10, you don't you can't create indexes on parent tables. As for the unique constraints, which are implemented using indexes, things get a bit complicated. So you have to ensure that the unique key contains the partition key, if you want to ensure uniqueness across all partitions, so you would create an index on the parent table to do that, and you have to make sure that you include the partition key, or otherwise you can't create a unique constraint that spans all partitions. You can still create unique indexes on each partition if you want a different unique constraint. So if Postgres had global indexes, which it doesn't have, then there wouldn't be this problem, because with global indexes, there's one index that covers data from all partitions. So, with global indexes, Postgres would be able to support unique constraints on that span partition tables that don't include the partition key, but we don't have that. So next is constraints. So just like indexes, each partition can have its own constraints, like check constraints or unique constraints or foreign keys. But it's more useful to define it, on the parent table, because managing constraints on each partition can be messy. So I just described unique constraints with indexes. So let's take a look at foreign keys. So foreign keys are supported on partition tables, but different versions have different levels of support. So for example, with version 11, you can create a foreign key on partition table, but it can only reference a non-partition table. But with version 12, you can even reference partition tables. So with version 12, I think the foreign keys are fully supported on partition tables. You can use them in the same way as you would use them with regular tables. Postgres doesn't support exclusion constraints on partition tables. So exclusion constraints allow you to do interesting things with just indexes, but with partitioning, you can no longer use those things, use those constraints. Next is triggers. So again, each partition can have its own triggers, just like it can have its own indexes and constraints. As for partition tables, statement level triggers could be defined from version 10, but row level triggers were not supported in version 10. So row level after triggers could be defined from version 11, and row level before triggers are only supported from version 13. So I think the reason why after row level triggers were implemented first was to implement foreign keys feature, which internally uses after row level triggers. Anyway, so next is logical replication. So partition tables did not play along well with logical replication until very recently. So you may know that to logically replicate a table, you have to add it to a publication object, and the subscription object on the receiving side will pick up a table with the same name and funnel all changes that are coming from the publication into the target table. So until version 13, you would have to replicate each partition one by one. But in version 13, you can simply add the partition table, that is the parent table, and all its partitions will be automatically replicated. So by default, this replication ships changes as if they were made directly to the partition. So the receiving side has to have the same partitions present. So here, if you look at the diagram, you can see that the original insert that is issued by the client is on the parent table, but it's logged into the replication log as insert on the partition, and the log gets replicated as is to the other side, and then it's inserted into the partition by the receiving side. With version 13, there's a new publication parameter called publish via partition root, which allows to publish the changes of partition tables as their own. So the receiving side doesn't have to worry about partitions. So as shown here, the insert on foo, while it is still logged into the replication log as insert on foo1, it is mapped back to the original operation and the original table and shipped as insert on the original table. So yeah, I mean, replication is more convenient with the latest Postgres. So if you if you find that useful, then you might find, might want to take a look at the latest release. So yeah, moving on to the optimizations that I think is an important part of the partitioning feature. So as you might know, partitioning is a very metadata heavy feature. So you have a partition key, you have partition bounds, and all of that is stored in the system catalogs. And Postgres uses that information to inform the query processing, the planner's decision making about queries that are issued on the partition tables. So first off, let's take a look at the most well-known feature called partition pruning. So partition pruning means pruning or not scanning partitions that are not relevant to the query. So whether or not a partition is relevant to the query is determined by the filters that are appearing in the query. So if the filter contains a column matching the partition key, then it can be used to prune partitions as shown here. So on the left-hand side, there is no filter. So the query scans all partitions, but on the right-hand side, there's a filter and it selects the partition to scan. So as I mentioned in the beginning, Postgres has long had a feature called constant exclusion, which underlied the pruning process. But in version 11, a new faster algorithm is now used for partition pruning. So the new algorithm is such that it can be invoked in more contexts than just during planning. So in version 11, pruning can also be performed using during query execution. For example, with prepared statements, a query is sometimes run using a cast plan. So the plan itself is made without any parameter values. So the planning cannot do any pruning. So the pruning has to occur when the plan is actually executed. So as you can see here, the subplans removed string is printed to show that the executor has removed some partitions using pruning. And runtime pruning is also more useful in more complex situations like nested loop join. So the inner relation of a nested loop join is a partition table. And you may know how nested loop join works. It takes a row from the outer relation, and using the join condition, it tries to match a row from the inner relation. If the join key matches the inner relation's partition key, the outer row's join key can be used to prune the inner partition tables. So in this example, the never executed text in the plan tells that none of the outer rows had to ever execute those index scans because the partitions to which those index can correspond were pruned for every outer row. So remember, before partition pruning was available, those index scans would be executed, but they would never return a hit because there would be no row in the inner relation that matches the outer row. But doing these index scans is wasteful because they never return a hit. With pruning, you use the partition pruning to avoid doing those scans in the first place. Excuse me. Next, I will describe some optimizations for more complex situations like joins. So Postgres 11 came with something called partition-wise joins, which converts an equijoin between two partition tables that are similarly partitioned into equijoins of their matching partitions. By equijoin, I mean equality condition. So consider this example. So we're joining tables foo and bar, which both have full range partitions with same range bounds. Without partition-wise join enabled, there will be a single join as highlighted in this plan, and joins input relations are the appends of foo and bar. So append represents the combined output of a partition table, if you didn't know that. And okay, just remember that this plan takes about 3 seconds. Next, once you enable partition-wise join by using the guc parameter enable partition-wise join, you can see a different plan shape. Now there are 4 joins where each is a join of partitions of foo and bar that have the same bounds. And finally, the append combines the output of the child joins. And you can see here that the execution time is about 1.8 seconds. So definitely an improvement. Next, if you enable parallel execution, these child joins are executed in parallel, which can further improve performance. Yeah. And by the way, this partition-wise join requires planner to spend extra cycles and memory, so it is disabled by default. So if you when experimenting, if you turn it on and see that it's it gives you faster plans, you may want to turn it on. But there was a limitation of partition-wise joins, that they can be only executed if the tables have same number of partitions and their bounds match exactly. So which can it can be a strict, too strict a requirement. In version 13, this restriction is no longer present. So for example, if I delete one of the partitions of bar, the query can still use partition-wise join with version 13. Now in this, when foo has 4 partitions, but bar has 3 partitions, the foo4 table partition doesn't have a joining partner on the bar side. So, and well, so it means that foo4's doesn't need to be joined with anything on the other side. So what happens effectively here is that foo4 partition has been pruned by joining. So next up is partition-wise grouping and aggregation. So similar stuff as I just described for joins. So an aggregate where the whole partition table is divided into smaller aggregates or individual partitions. And if it's not a grouped aggregate, then the partition level aggregates are only partial, which must be combined to get the final aggregate result. So you can see here that there's definitely an improvement in performance, but not as significant as it was with join. And if the aggregate is grouped and the grouping key matches the partition key, then the grouping itself can be performed on the partition level along with the aggregate, as you can see here. So when both the grouping and aggregation can be performed on individual partitions, there is no need for finalized aggregate, because each group is limited to each partition, and the group doesn't need to consider other partitions, because data is mutually exclusive between partitions. And just like partition-wise joins, making an partition-wise aggregation plan is also CPU and memory intensive, so it is disabled by default. Again, if you find that it's producing better plans, you might want to turn it on. Finally, there's one more smart thing that the planner does that is based on partitioning. If there is an order by clause whose key matches a range partition table's partition key, then some needless sorting can be avoided. On the left, you can see that sorted scans of partitions using indexes are being merged to get the final result. But this merging is redundant because range partitions are ordered among themselves. So from version 12, if the planner sees this, then it avoids doing the merge, and it can definitely be much faster. So that's all the partitioning optimizations I know. So let's move on to some other stuff. All right. So I think I would like to end this talk with some by discussing some tips on partitioning that you might find useful to remember. So first, partition key. How do you find what set of columns will constitute a good partition key? So first, consider if you have a requirement of a periodic batch deletion, and if you are using delete for that, just take a look at what the where clause was for those deletes, and those columns in the deletes where filters are good candidates for partition key. Remember, one of the main reasons to implement partitioning is to optimize this, delete and insert workflow. So looking at that first might be a good idea. And if this workflow is not that important to you, you consider performance to be more important, then take a look at the work clauses of the queries that you want to optimize, and there will be a column that will almost always be there, and that will be your partition key. But a thing that complicates this choice is whether you need a unique constraint on the table. And as discussed before, this unique key has to have the partition key. So you have to consider that when choosing the partition key. So in most cases, you should be able to design your table such that all of the above requirements, the delete workflow, performance, and unique constraint requirements don't conflict with each other. And if that happens, then good. So next, let's take a look at what partition methods to use. So this often falls out of the design of the partition key, but there can be some independent concerns. And yeah, so you might want to use range if the partition key is of a type whose values have some natural ordering, such as date and time. And range partitioning is good for optimizing range queries that use inequality operators like greater than, less than. And so if you have those queries and that you want to optimize, then range might be good for you. Use list if there are only few values that the application cares about. In fact, so few that you can list those values by hand to the values for each partition by hand, then list partitioning might be good. So for comparison with range, there are so many values that you can't list each value individually. So you specify a summary in the form of min and max for each partition. With list partitioning, you can only expect mainly the equality queries to be optimized. So use hash if none of those things, none of the columns qualify for range and list, but you would still like to distribute your data. And finally, you need to also consider how many partitions there will be. In short, avoid extremes. So the design decisions regarding the partition key and partitioning method will affect how many partitions will result from that design. For example, you might start using list partitioning with one value for each partition because right now there are only few values to consider. But you may turn out to be wrong about how many values there will be, and suddenly you might end up with too many partitions, and you don't want that to happen. So it might be a good idea to foresee that and use hash partitioning or range partitioning instead of list partitioning. So the point is, you have to consider in your design how many partitions there will be, and try to avoid the extreme too few or too many partitions. So in general, if your design results in like thousands of partitions, you may have things to worry about. So while simple queries that are that map well to your partition key, they can become faster. Having too many partitions can make things quite slow for other queries and some of the other things. So yeah, I mean, in any case, you have to experiment a bit to get to the right design in terms of partition key, partition method, and number of partitions. It would have been nice if there was some automatic advisor kind of stuff in partitioning, but currently our options are limited. I think something called HypoPG have some features for this, but I haven't looked at it very closely. So you might want to take a look at it. So anyway, I think that's all I got. Thanks for listening. If you have any questions, I will take them. Hi. So I see a question here in the questions and answers. Can you hear me? Shit. So I see a question I see a question on a limit on number of partitions, and I just described in the last best practices section to avoid extremes, like if your design results in thousands of partitions, you have to consider that it might affect the performance on things that are not that don't map well with your partitioning design. And yeah, the second question is, like, are there any plans to add maintenance functions to core, like pg-partman, and like automatic partition creation, data moving? So I'm not sure if anyone is working on that at the moment, but there is certainly a requirement for that, and it's possible that somebody might take it up in the future. So there is one more question here. So it says inheritance partitioning uses it. Why to use inheritance partitioning if it can provide partition pruning? Well, I mean, you can get the same effect as partition pruning by something called constraint exclusion, but I would suggest that it's not a good idea to use inheritance to implement partitioning, because you have a partitioning feature to do that. So there's a question which says, what needs to be done to enforce global constraints when using partitions in version 11? So as I mentioned, you just have to create an index on the parent whose key contains the partition key columns. So if, for example, you have a table foo with column A and you want to create a unique constraint on the A column, then you can only do that if your partition key is also A, and simply create a unique index on the parent table on that column, and that will give you the global constraint. Yeah. As I also mentioned, the global constraints on some other columns that don't include partition key are not supported. Do we have more questions? Please write them in the questions and answers.